virtually or physically. So I'm very excited that Dylan also agreed to give a tutorial. So Dylan has done fantastic recent work at on the theoretical foundations of reinforcement learning. And so today he's gonna give the morning session tutorials on theoretical foundations of reinforcement learning. And this is gonna be sort of like a preparatory tutorial for the afternoon tutorial, where we're gonna also go into multi-agent reinforcement learning, which is one of the themes of the semester. So thank you very much, Dylan, and looking forward. Yeah, and if you have a, oh, okay, good.
I didn't quite hear that last part, but should I begin?
Yes.
All right, great. Yeah, so, thanks for having me. Yeah, as Vasila said, I'm going to be talking about sort of recent progress on the theoretical foundations of RL. And, this is a workshop about learning in games. This is going to be focused almost entirely on learning and not so much on games. But yeah, the point is to sort of give the necessary background for Chi's tutorial later in the afternoon, which will build on this. And yeah, let me just say, we should have time. Feel free to interrupt if you have questions. So let's get started. So this talk, we're focusing on the theoretical foundations of RL, but I'm going to be doing this from something like a machine learning or like a statistical learning perspective. And if you're new to RL, the way I'd summarize the difference between these is to say, machine learning is about predicting patterns, whereas reinforcement learning is about using data to make decisions. And so when I say predicting patterns, I'm talking about these domains where we've seen, huge breakthroughs in the last decade, like, computer vision, machine translation, where machine learning is allowing us to process massive amounts of data and extract patterns like, what features of this image correspond to a cat or a dog. But when I say making decisions, I'm talking about tasks like picking what treatment we should give to a patient based on their medical stats, or what signals we should send to our robots' actuators based on what we're currently seeing on our camera. And so the excitement about RL, this is really about the fact that it gives us a paradigm that we can use to move beyond just predicting patterns to building AI systems that can act on these predictions or act on data to make decisions. And so the first thing I'm going to do, because it'll be something like a running theme in this tutorial, is to go into a bit more depth in illustrating the differences between ML and decision making, so like RL, but also some parallels. So I'm actually going to walk through 3 different problems. The first will be the classical supervised learning problem, and then we'll look at the contextual bandit problem and the reinforcement learning problem. And so I like to think of these as sort of points on a spectrum of problems where we're adding additional interactivity and feedback on top of basic supervised learning. And yeah, contextual bandits and RL, these are what I would call interactive decision-making problems. So let's start with supervised learning. So I'm going to try to describe how we use supervised learning to solve new problems when we encounter them in the wild. And we'll look at this in 3 steps. So the first step will be that we will pick a class of what we'll call like models or hypotheses that are trying to capture our prior knowledge about the world or about the problem we're trying to solve. So for vision, we might think convolutional neural nets capture our prior knowledge well. For text classification, we might think linear models maybe work well. But we're going to take this as a given. Then in the next step, we're going to gather a data set consisting of examples. So like X is a feature vector here, Y is a label. And then the last step, we're just going to find a model that fits this data set well. And we'll return this, and usually the hope will be that it will generalize well to future examples. So supervised learning is a purely passive problem. The contextual bandit, which I said is kind of like the next step up, this is an online or sequential problem where now we have to actively make decisions on the fly in an unknown environment. And so the setup is, at each time, if we're the learner, we'll receive what's called like a context, or you can think of it as like a feature vector xt. We'll select an action or a treatment at, and then we'll receive a reward rt for the action we take. And our goal will be to pick these actions so that we maximize the total reward. But to make this a little more concrete, if we think about something like personalized medicine, here we can think of this as each time we have a patient arriving, we look at their medical stats, which could be like this context. Our action will be the treatment we propose, and the patient's response will be our reward. So we can sort of use this model to find personalized treatment policies based on responses. But you might be wondering at this point, well, okay, what does this have to do with supervised learning? What ties these problems together is the fact that we would like to work with models. So when we design algorithms, we want to be able to use function approximation to capture things like rewards or treatment effects. Like if I have a particular patient and I take a particular action, what's their response? But the environment is going to be unknown to us, so we don't know what model is going to work well in advance, so we need to learn this from data as we're making our decisions. Okay, and a really important detail, which I didn't mention so far, is in the Contextual Bandit, we're not allowing our actions to influence how this context is evolving. But if we do allow our actions to influence the context, we call it a state instead. And this brings us to precisely the reinforcement learning problem. So this can be a better model for domains like, say, robotics, where the actions we're taking have long-term impacts on like how our system evolves. But this is a harder problem because it requires kind of like long-term planning. So we need to be able to explore our system and figure out, how do we get from point A to point B. And again, just like in supervised learning and contextual bandits, we want to be able to learn models from data here as well. But now we're typically going to want a model to capture things like long-term rewards, or what are the dynamics of the environment that our agent lives in. So altogether, we kind of have this hierarchy of problems. What I claim is, and this is going to motivate a lot of the results we'll go over in the tutorial, there are some big gaps between our capabilities for supervised learning and for reinforcement learning, and more broadly, decision-making. And I'll just briefly give a taste for why this is. So machine learning, as we've already discussed, this is great at prediction problems. Like if I want to predict, do images contain cats or dogs? I have lots of data where I know the right answer for every example. Machine learning is great at processing this data to make predictions. But where we run into issues is in RL and decision making, we want to act on these predictions to make decisions, like what treatment to give. And this introduces feedback loops. And these are what really bring a lot of the challenges to the picture. So for starters, once we have feedback loops, the decisions we make can influence kind of what data we actually get to collect. And this introduces like the need for counterfactual reasoning. The point being, if we think about, say, like medicine, we only get to see the outcome for the particular treatment we prescribe. And what we really care about is what would have happened if we had selected our treatment differently. But going even further though, again, if we think back to these domains like robotics, the decisions we make are influencing the state of the world that generates our data. And we really have to be strategic to control how this state evolves. And so altogether, the consequence of these feedback loops is if we try to naively apply machine learning techniques to RL and decision-making without accounting for things like counterfactuals or long-term impact, we end up with models that have high error, and we make bad decisions. So the point of this tutorial is to kind of give an overview of the algorithmic principles that we can use to get a handle on these feedback loops and hopefully make good decisions. So this is going to have a couple of parts. The first thing we're going to do is just go through basic concepts and solutions, like how do we set up the RL problem formally? What are basic challenges that any algorithm needs to address, like exploration and generalization? And building on these issues, the focus sort of later in the tutorial will be to try to get up to speed on our current understanding of the statistical landscape of reinforcement learning. Like what assumptions do we need to make on the environment we're trying to learn to control? What algorithm design principles do we need if we want to attain sample efficient algorithms for RL? And this is going to be mostly focused on sort of the statistical aspects of RL and less focused on computation, though we will touch on some of these issues. And of course, the real goal here is to get you prepared for Chi's tutorial, which is going to build on these ideas in the multi-agent setting. So that's kind of the game plan. And so let's dive in. So I'll start by getting through just the introductory concepts, but I'll give kind of a more refined outline for the talk once we have these out of the way. So I want to start by formalizing the reinforcement learning problem. In this tutorial, we're going to work in what I'll call like an episodic reinforcement learning setting. And when I say episodic, you should think of a setting where I get to run my robot for a bit and then stop and reset it back to its starting position. So the way we'll set this up is our agent will live in what's called a Markov decision process. And this is going to evolve as follows. So we're going to have an initial state, which is called x1. And this will be drawn from an initial state distribution, d1. And then we're going to run for big H steps. So big H in this talk is what we'll call the horizon. This is like the length of an episode. And in each step in a given episode, we're first going to look at the current state, which will be denoted xh. So script x here is what we'll call the state space. We're going to select an action to take based on the current state, which we'll denote by a sub h. So script a is going to be our action space. Then two things will happen. So first, we'll receive a reward based on the state we're in and the action we took. And then we will see a transition to the next state. So our system will evolve. And again, this will be based on the current state and what action we took. So that's one step. And we're going to keep doing this until we reach the end of the episode. And the task we're interested in here is, how do we maximize our total reward across the whole episode? That is, we want to find a policy, which is just a mapping from states to actions that maximizes this expected total reward function, which we'll call jpi. So just a note on notation, E superscript pi in this talk will denote like expectation under this process where our MDP evolves with actions selected according to the policy pi. So that's the basic goal, is maximizing our rewards. But I haven't said anything about like learning yet. How do we set this up as a learning problem? Well, what we're going to do is we're going to assume that initially this MDP is unknown to us. So the only way we actually get information is by running policies or selecting actions and seeing the resulting sequence of states and rewards. And so, which we'll call a trajectory in this talk, by the way. So trajectory is like all the data we see when we do an episode of our Markov decision process. In particular, though, the way we'll set this up is we get to run for capital T episodes. So capital T is the number of episodes. And now I'm using superscript little t to denote what episode we're in. And so we want to learn a good policy by running for many episodes. And there's a couple ways you can formalize what it means to do this. So the first model, which is often called PAC-RL, like PAC means probably approximately correct, just like in statistical learning. And this is, we're going to run for a bunch of episodes, then we're going to output a policy, and we want this policy to be epsilon close to optimal. And ideally, we'd like to do this using as few episodes as possible. Another notion we can look at is what's called regret. And this is where we're going to look at cumulative suboptimality across all of these episodes. So like not just how good the final policy is, but how good are we doing along the way. And I'm using pi star here to denote the optimal policy, which I don't know. And so the goal in this regret setup is usually we want our regret to be sublinear in T, like say root T, which means that if we look at our average performance, this is converging to optimal asymptotically. And I'll just say, regret and PAC, these can actually be reduced between one another. And you only lose a little bit in terms of either dependence on epsilon or dependence on T in doing this. So for this tutorial, we're going to work with whichever one is sort of convenient for presenting certain results. Let me double check on the question.
There's a question.
Oh yeah. This is a question. To be clear, the state space is not a DAG. yeah, we're not going to assume it's a DAG in this tutorial, but there's really not a lot of loss of generality by doing this, unless you care about, precise dependence on like this parameter H in the sorts of learning guarantees you're looking for. Okay, let me just say a couple more notes about this model. So there's many variations you can consider. We were sort of looking at mini small episodes. You can imagine instead looking at like one giant, very long episode, like a single trajectory. You can also look at settings where, maybe you have an infinite horizon and the game just stops once you reach some goal state. Another thing to be aware of is, we're weighting rewards uniformly. It's also very common to discount future rewards based on how far off they are, which is useful when you look at infinite horizon problems. And these are all good concepts to be familiar with if you want to go through and like digest the literature and compare results. But we're focusing on the episodic setting because it's sort of the simplest conceptually, but it really captures the essential statistical considerations. Okay, and on that note, as I mentioned, our goal is to sort of learn in a sample efficient manner. And so this means finding a near optimal policy with as few episodes as possible. And I'm going to try to give a sense here for what it means to be sample efficient. So we're going to look at a pretty simple example, which is going to be an MDP where the state space is structured as a tree with exponentially many leaves. So let's say we have only 2 actions to start. We're going to start off at the root of the tree, like that's the initial state. And each action we take will choose whether we go left or right in the tree. But the trick is we're going to make it so that only a single leaf in this tree has a reward. All the others have 0 reward. And what you'll see is there's essentially no way for us to do better than explicitly trying every path through the tree until we get a reward. Or in other words, the sample complexity for this problem, like the number of episodes we need to do to learn a good policy, this is going to be exponential in the horizon. So exponential sample complexity, this is not great if we're trying to attack, like say, real world problems. And so the conceptual takeaway here is we need to make additional modeling assumptions if we want to be able to, design interesting algorithms and get interesting guarantees. And so you should really think of RL as not just one problem, but a family of problems depending on, exactly what assumptions we make. And we'll see many examples of modeling assumptions later on. But before looking at that, I want to cover some features that will be common across all these different settings. Yes, Kostas, this is linear in the cardinality of the state space. And I'll say more about the cardinality of the state space as we go on as well, because in some sense, this is also something we would like to avoid. Cool. So the viewpoint we're going to adopt in this tutorial, which I believe this originally came from John Langford, is we're going to break sample efficient learning into sort of 3 key challenges. And we're going to call these credit assignment, exploration, and generalization. I'm going to go over each of these challenges individually, and the point will be somehow that any full solution to the reinforcement learning problem needs to put all of these together. Okay, let's first look at credit assignment. So credit assignment is asking, let's say I take a series of actions where I'm trying to get through a maze, but I hit a dead end or I run out of time and I don't reach my goal. So how do I figure out which of these actions was wrong? Or in other words, how do I assign credit for the final outcome to each individual action to figure out which ones were good and bad? There's a classical solution to this problem, which is what's called dynamic programming. And this is an approach that allows us to solve what's called the planning problem, which means, let's say we know the rewards and transition probabilities, and we just want to calculate the optimal policy. So there's no uncertainty here. And the basic idea is, let's say we're trying to solve a maze. We'll start at the goal state. And for each of the states that neighbor the goal, we'll check what's the optimal action to get us toward the goal. And then for the neighbors of these states, we're going to repeat the same process, and we're going to keep doing this recursively. And okay, So to explain this formally, we're going to introduce what are called value functions, or like reward to go functions. And this is a concept we're going to use throughout the talk. So the optimal state value function, which we'll call V star here, this is asking, what is the reward I get if I start in state X at time H and then follow the optimal policy pi star until the end of the episode? So it's like the reward to go at state X if I follow pi star. And then you can similarly define what's called the state action value function, which we're calling Q star. These are also sometimes called Q functions. And this is very similar. It's just asking, suppose I start in state X, then take action A, and then follow pi star until the end of the episode. What's the reward that I get? And I'll just briefly mention, because this will come up later, you can imagine defining analogous value functions for policies besides pi star, and we'll denote these by Q pi and V pi. So let's look at dynamic programming. Dynamic programming is going to give us a way to compute these value functions. And the point will be that once we have these, we can easily back out the optimal policy. So we'll start off by setting V star H plus 1 to 0. This is saying, like, once the episode's over, there's no more reward to go. And then we're going to apply what's called the Bellman equation. And this, or like Bellman's optimality principle, this is just saying for each little h, let's imagine that I've already computed V star for little h plus 1. So if I know this, then Q star h of xa, this is just the expected value of my reward for the current step, plus the expected value of V star h plus 1 under the next state evolution. So that gives me Q star. Once I have Q star, V star is just the max of Q star, and the optimal policy is just the argmax for Q star. And one quick note here is, like, because we have a finite horizon, the optimal policies in this setting are going to depend on the horizon in general. So that's why I have this H subscript here. Okay. So this is great. But we'll note that this requires two things. This requires that I know the system's dynamics, or the transition probabilities, so that I can compute this expectation. And naively, this also is going to require that I, like, enumerate over all the states, so I can compute, Q star of XA for all XA pairs. So both of these are kind of problematic if we're only accessing our system through running policies and seeing the outcomes. And so you shouldn't think of this as a solution to learning with an unknown system. Just think of it as a way to plan or optimize if you already know the system. But we will build on this. All right, that's credit assignment. Let's move on next to the next challenge, which is exploration. Exploration is asking, okay, given that I'm in this unknown environment, how should I select my actions so that I can gather data that will help me to learn more about this environment? So the simplest setting we can look at, which exemplifies this issue, is what's called the multi-orange bandit problem. And this is the special case of reinforcement learning where we have horizon 1, and we also just have a single state. So for example, you can think about a setting where I have some patient and my action is a treatment that I'm trying to recommend to the patient to help them feel better. And here I'm just visualizing the reward distribution for each treatment. And so the basic issue we see here is, we only see the response for the particular treatment we propose. Like if we give ibuprofen, we don't see how, we see how the patient responds to this, but we don't see how they would have responded to other treatments. And this means we have sort of a trade-off between gathering data and exploiting what we already know. So exploiting on one hand means, greedily taking actions we think are good given the data we've gathered so far. Exploring means selecting actions we've seen less of so that we can, maybe better estimate their rewards in the future. So let's look at a classical approach to dealing with this problem. This is going to be called the upper confidence bound, or UCB algorithm. And the idea here is, let's say I'm at a given, like let's say I've already interacted for some number of rounds. I've collected a bunch of rewards. Given all of these rewards I've collected, I'm going to estimate the mean reward for each action and build confidence intervals around this. And then I'm just going to pull the action or play the action that has the highest upper confidence bound. This kind of balances exploration and exploitation implicitly because we either get a large reward or shrink a large confidence interval. And what you can show is that the number of rounds this approach needs, or I should say episodes, but an episode here only has length 1. The number of episodes this approach needs to find an epsilon suboptimal policy is number of actions over epsilon squared, and the regret scales as root AT. So in both cases, we're kind of linear in the number of actions, and the dependence on epsilon and t that you see, you can think of as coming from like statistical deviations. And I'm actually going to spend a minute sketching how we prove this algorithm works because we're going to build on this to look at solutions for more complex problems. So I'll start by formally describing this algorithm. So if we're at episode or round t, we're going to let nt of a denote the number of times we've played action A, and we'll let f hat t denote the sample means from the data we've collected so far. And then for each arm, we'll define what I'll call an upper confidence bound, f bar t, and this is going to be the sample mean plus a bonus function that depends on the arm. And this bonus is going to be set proportional to root 1 over the number of pulls for that particular arm or action. And once we have this, we're just going to pull the action that maximizes f bar t. Okay, so the idea here is f bar t, I'm going to prove this now. This is kind of like an upper confidence bound. So this is going to always upper bound f star. And so this is why we call this Ucbvi, right? But I'll break this into a couple of steps. And the first step of the proof will be to show that f bar t is indeed an upper confidence bound. And this is a property that we sometimes call optimism. Like f bar t is optimistic about what the outcome will be because it always thinks it will be better than the true outcome. So we're going to look at the Azuma-Hufting inequality, which is this basic concentration bound. And this is an inequality that says if I have a sequence of random variables z1 through zn, and I look at the average distance between their sum of these variables and the sum of their conditional expectations, the scales is 1 over root n with high probability. So to come back to the bandit problem, we're going to let f star of a denote the mean reward function for action A. And what Hufting will tell us is that time t, if we look at the error between f hat t and f star, the scales as root 1 over nt of a. And I'll just mention here, I'm going to be imprecise about log factors and this sort of thing in this talk. Okay. So the idea here is that the distance between these functions is proportional to root 1 over nt of a. And so because we set this bonus here also proportional to root 1 over nt, the bonus is going to cancel out this error. And so we'll be guaranteed that f bar t is optimistic. It upper bounds f star. Okay. And so why is this good? Well, the point of optimism is that we'll be able to prove that our suboptimality is dominated by the bonus for the action that we play. So if we look at the max value of f star, like the optimal reward minus f star of at, we're going to be able to upper bound this by the max value of f bar t using the optimism property. And because at was chosen to maximize the upper confidence bound, this is the same as f bar t of at minus f star of at. And so at this point, we're in really good shape because this is just the error of our estimate on a particular action. And so we'll actually be able to bound this up to a factor of 2, again, by this bonus itself, this root 1 over nt of a. And so finally, we can sum this error across all of our rounds or across all of our episodes. And using kind of a pigeonhole type argument, which I'll leave for you to work out yourself, you'll be able to show that this sum of root 1 over nt's scales as root number of actions times t, which gives the regret bound we wanted. And that's it. Really, the key here is because we're optimistic, our error is controlled by the range of these bonuses, but only for the actions we play. And that's good because it means if we play an action and it has bad reward, the bonus has to be big. But every time this happens, like the counter for that action increments, and this can only happen so many times without the bonus, shrinking by a lot. Okay, and I'll just briefly mention there's another simpler method which is good to be aware of called epsilon greedy. And this is just an algorithm that says estimate the rewards. Most of the time you just play the action that our estimated reward function thinks is good, and otherwise you explore uniformly at random. So this actually is the same sample complexity, but it has slightly worse regret. But like the real issue, which we'll see later, is it doesn't generalize very well to more complicated problems. Okay, let's move on to the last of these core challenges, which is generalization. So generalization is asking, so now that I've gathered a bunch of data consisting of like observations and outcomes, how can I learn concepts from this data that will allow me to act on observations that I've never seen before? So one way we can address this issue is to revisit this supervised learning setting from the intro, though this time from a slightly more technical perspective. So in supervised learning, I have this data set consisting of past examples, and I'm going to fit a model using this, like what I'm calling a model class or hypothesis class script F. This is going to give me a hypothesis that I can use to make predictions on future examples. And the natural question to ask here is, when is this approach going to be successful at generalizing to future examples? And so what the theory of statistical learning provides is complexity measures that allow us to quantify how successful we are at generalizing. And I'm just going to give a representative result here. And this will be for what's called empirical risk minimization, which is one of the most ubiquitous supervised learning algorithms. So this is just the algorithm that finds the hypothesis with the lowest error on our training data, and then returns this, and that's it. And so what statistical learning tells us is, if our data is IID, then empirical risk minimization, even though it only looks at training data, its prediction error on future examples is just as good as if we knew the true distribution, up to some error term which is going to 0 as we get more samples. Oh, so n is the number of samples here. And the interesting thing to focus on in this bound is what I'm calling comp of script F here. And this will be a notion of like statistical capacity or complexity that reflects how rich our function class is. And I'll give a taste for what this looks like. So perhaps the most well-known notion of capacity in statistical learning is what's called VC dimension, which you may have seen before. There are many others, that are, you can look at, like there's, it's called Rademacher complexity or covering number. All of these give notions of how flexible a function class is. And these are all sort of necessary and sufficient for learning in different worst case senses. And I'm not going to use any of these concepts in detail in this talk. I'll be very sketchy about this. So I'll just give a couple of examples that we can revisit. So if you have a finite class of functions, you can take this capacity to scale with log number of functions. And if you have a linear hypothesis class, then there are complexity measures that scale either with like the dimension, like the number of features, or on the magnitude of the weights, depending on the model. But the key point is that all of these complexity measures, they don't explicitly depend on the size of the observation space or like the feature space, or for RL, like the state space. These only care about how expressive your function class is once you project it onto whatever the sort of feature space is. And this is reflecting the fact that you're generalizing. And so one idea I want to come back to before moving on is, well, why do we care about using flexible model classes and generalizing? And the point is, if we look at like typical RL applications, here we usually have states that are going to be like rich and high dimensional. Like in robotics, the states I have could be raw pixels from a camera. And so the point is, we want to be able to use flexible models or hypothesis classes to avoid paying for the size of our state space, or like paying for the curse of dimensionality. And in general, what choice of model or hypothesis class works well, this will be something that's like domain specific. It could be neural nets, it could be forests, it really depends. But something I found in my own research is that if we think about what capabilities and understanding we have for dealing with these sorts of flexible models or hypotheses in supervised learning, and then ask what happens when we try to get similar capabilities for reinforcement learning, this leads to a lot of really interesting research questions, okay? So I'll just mention a couple of these quickly. So the first one is algorithm design. So like, how can we get general purpose algorithms that work with any sort of like class of models or hypotheses? In supervised learning, we saw this principle ERM, just taking the model that fits your data best. And this can be applied universally to any type of hypothesis class. But for RL and like more broadly decision-making, algorithm design, at least on the theoretical front, has mostly proceeded on a kind of case-by-case basis, where we're designing new algorithms for all the different models. Like every time we get a new model, we might want to experiment with. And so given all the different types of hypothesis classes there are, really what we'd like is algorithms that can take this hypothesis class as an input and start making accurate decisions out of the box. So the other major research question I'll mention here is sample complexity, like understanding how many samples are necessary and sufficient to learn for your problem. Like in supervised learning, we saw these complexity measures like VC dimension. These give rates of convergence, and they also give fundamental limits on how many samples you need to learn, at least in the worst case. Beyond the worst case is still a very active area of research. But in decision-making, understanding sample complexity, this is very much tied to algorithm design. And as such, a lot of our understanding on the theoretical side is very case by case. And so I think it's really interesting here to understand how this classical curve of like risk versus amount of data, how this changes as we add interactivity to the picture and vary how complex our interactive learning problem is. Okay, that was a lot to say about generalization. So let's come back to the big picture. We have these three key challenges, and the idea is somehow any full solution to the RL problem somehow needs to put all of these together. We saw that we have solutions to all of these individual problems. And in fact, a lot of these are essentially classical, but where things get tricky is when we start to combine them. And so what it'll turn out is like for any pair of these challenges, we actually have solutions here as well, although these are somewhat more recent. So for example, if we want generalization and exploration, but only for a short horizon, this gives contextual bandits. But when you try to solve all three of these challenges simultaneously, this is where we really get to like the frontier for RL theory. So with that in mind, the remainder for the roadmap, or the roadmap for the remainder of the tutorial is going to be the first, we're going to look at, well, how do you solve all these challenges in pairs and what are the solutions? And then building on this, in the second part of the tutorial, I'll try to give the lay of the land for when we want to solve all three simultaneously. Okay, so let's start going through these sort of intermediate level challenges. And the first of these that we're going to look at is how do we combine exploration and credit assignment when we don't worry about generalizing across states. So this is going to correspond to a problem setting that we call tabular reinforcement learning. And what this means is reinforcement learning with a long horizon, like big H. So I still care about credit assignment, but we have a small finite state and action space. And the idea here is because we're assuming the number of states and actions is small, we'll be able to explicitly learn what to do in every state directly. We won't have to worry about generalizing between states. But even though we don't care about generalization here, this is still a non-trivial problem in the sense that if we think about these environments like mazes or combination locks, where there's maybe a single path that gets you towards the goal, just exploring actions uniformly will take an exponential number of tries until we sample the right path. And to beat this we have to be deliberate in how we explore. So I'm going to describe a, I think, pretty elegant solution to this problem, which is called the Ucbvi algorithm. And this stands for upper confidence bound value iteration. So as the name suggests, this is just combining two techniques we've already seen, optimism and dynamic programming. And I'll just describe what this algorithm does in a given episode. So there's a bunch of quantities we kind of need to compute before I tell you the core of the algorithm. The first thing we're going to do is compute counts. So nt of x prime here is asking how many times in the data I've seen so far did I get to state X, take action A, and then C, state X prime. And then analogously, nt of xa is just how many times did I visit state X and take action A. So once we have these counts, we're going to use them to estimate the transition probabilities. And we're also going to take the sample mean for each state action pair. So this will be called f hat t. F star of xa here is denoting the true mean reward for a given state in action. Okay, and the last thing we're going to do here is, similar to the bandit, we'll define a bonus, but now for each state in action. So the bonus for action xa is proportional to root 1 over the visitation count for x and a. So now that we have these quantities defined, I can tell you the main idea behind the algorithm, and this is very simple. So we're just going to do value iteration or dynamic programming with our estimated rewards and transitions. But the only catch is we're going to add these bonuses to the rewards. And the idea is this will encourage us to visit new states and actions. So if we just walk through in a little bit more detail what this value iteration looks like, we're going to have these functions q bar and v bar, which will denote our optimistic estimates for the true q functions and value functions. So we're starting just like in regular dynamic programming with v bar h plus 1 equal to 0. And at each step, we're setting q bar h of xa to be the mean reward for the state in action, plus the bonus for the state in action, plus the expected value of v bar h plus 1, but under our estimated transition probabilities. Okay, so we keep doing that. And once we have these optimistic q functions, we're going to just play the policy that optimizes the q function. So what you can show for this approach is we have regret that scales linearly in the horizon, and then with the square root of the number of states times the number of actions times the number of episodes. So this is actually minimax optimal, but the conceptual takeaway I want to focus on is we're polynomial in all the parameters, like number of time horizon, number of actions, number of states. And this is reflecting the fact that we're systematically exploring the unknown MDP. So naive exploration here would have, say, exponential in the horizon in the sample complexity you get. I'll briefly mention, this follows a pretty long line of research. So, the first few works here were mainly focused with, well, how do we get sample complexity that's polynomial at all? And this has gradually been brought down to the rate I'm showing here, which is like the minimax rate. With all these approaches, though, I'll just mention, these are what people typically refer to as like model-based. And this is referring to the fact that they're explicitly estimating the transition probabilities. You can also look at what are called model-free methods, which just try to directly estimate the Q functions without estimating probabilities. And you can actually get similar regret bounds here. But with all of these approaches, you're still memorizing like at least one number for all the states. So that you're not generalizing across states. Okay, let's briefly go into how you prove this regret bound for Ucbvi. And the first step in the proof, just like for bandits, will be to show that our Q functions Q bar are optimistic in the sense that they upper bound Q star everywhere. So let's look at the difference between Q star and Q bar at step H, which we want to bound by 0. And we're going to use the Bellman optimality condition to relate this difference to the difference in the next step Q functions. So the idea is, because Q star satisfies the Bellman equation, we can write this difference in terms of the statistical error between our rewards and transitions. So let's remember f star here is the mean reward function. So error of xa is just f star minus f hat plus p minus p hat. So we have this error term. We're subtracting off the bonus because the bonus was added to q bar. And then we have the expected difference between v star and v bar at the next step under the true model. And so the idea here is if we use like concentration, just like we did for bandits, we can show that the bonus will dominate the error term. So we can write this off as 0. And that's just going to leave us with the difference between v star and v bar at the next step. But the idea is like by the inductive hypothesis, we're actually done because we're assuming that q bar is optimistic for the next step. So this is also at most 0. Okay, and then once we have optimism, there are just a couple more steps. The first one I won't go into detail about here, but the point will be that using similar reasoning to the bandit case, we can use optimism to show that our suboptimality in a given episode is bounded by the sum of the bonuses in this episode. Okay, and then if we look at regret, we're just going to get the sum of bonuses over all the episodes, and if you remember how the bonuses are defined, this is just going to be the like sum over t, sum over h, root 1 over the like count for the state and action I visited. And because we have finite state actions again, the count for each state and action can only shrink so much. So again, using like a pigeonhole type argument, you can show that this scales as like root number of states, number of actions times t, and that's it. Obviously, if you really care about the dependence on h here, you need to be a little more careful, but that's sort of a second order issue. Okay, let's move on. So that was all I wanted to say about tabular RL. And the point for tabular RL was we're solving exploration in the MDP setting with a long horizon, but the catch was we had this finite state space. So we can afford to learn the dynamics or the value function just by memorization in every state. What we're going to do now is come back to the contextual bandit problem. And the point of the contextual bandit problem will be to incorporate generalization. So this is a setting, if you remember from the intro, where it's RL with horizon 1. So there's no credit assignment. But now we do need to worry about generalizing over contexts, which are what we call the states in this setting. The contexts are just states and we have horizon 1. And to make this idea kind of concrete, let's think about if we're trying to recommend medical treatments to patients. The context here could represent information about a specific patient we're trying to treat. And a particular patient will have their own profile of rewards for each treatment, just like in the multi-armed bandit. But unlike in the regular multi-armed bandit, we're going to move from one patient to another or one context to another. And a new patient might have a profile of rewards that looks quite different from the last patient, and others might be somewhere in between. So in general, we can take the mean reward for each action or treatment, and we can plot how this varies as we go from patient to patient or context to context. And this is going to give us a full reward landscape where we have potentially high dimensional covariates or contexts as one axis and actions as the other axis. And I find this landscape view really useful to illustrate why this setting captures both exploration and generalization. So on one hand, we have to explore because we're only getting limited feedback. Like if we see this user right here and we recommend a particular treatment, we only see the feedback at a particular point on the landscape where the axes meet. So we don't see the reward function anywhere else. So we still need to be deliberate about how we're gathering data, because if we just say like run supervised learning on the data we gather, it might have bias or it might be misleading for places we haven't covered. But on the other hand, we still need to worry about generalization because this context space is high dimensional and complex. Like we may never see the exact same context twice. So we will not have enough samples to get away with just memorizing what to do for each user. Instead, somehow we need to propagate information across this landscape so that we can generalize and be intelligent about how to explore and exploit even for unseen contexts. So I'm going to describe a couple of approaches to solving this challenge of generalization and exploration. And for both of these approaches, we'll take a modeling perspective and assume that we have access to a candidate class of reward functions that's flexible enough to contain like the true unknown mean reward function. So we're going to assume that we have a hypothesis class script f that contains this function f star of xa, which is just denoting like the average kind of reward landscape here, like the landscape of our average rewards for each context and action. And we're calling script f here a model class or a hypothesis class because just like in supervised learning, this is a model that's capturing our prior knowledge about like the domain at hand, about like what we think the landscape might look like. And I'll just briefly mention this assumption that we have a hypothesis class that contains like somehow the true reward function. This is often called realizability, and we're going to use this later in the talk. Okay, so one way you can try to solve this setting is to use optimism, as we've been doing so far, and directly maybe generalize the multi-armed bandit approach we saw in the first part of the talk. So we could try to construct something like a UCB function that upper bounds the true reward for all contexts and actions. And then, once I have a context, I can just take the action that has the highest UCB here. So for example, if you have a linear model where f star is linear in some fixed context action feature map in D dimensions, there's an algorithm called LinUCB that does exactly this, right? It just estimates a linear model, builds an upper confidence bound, pulls the action that maximizes this. And you can show that the regret of this method, it scales with the dimension of the feature map and not the number of contexts or actions. So you are generalizing here. But fundamentally, the reason why this works is because linear models let you extrapolate. Like once you've explored a full basis worth of directions, you have a good estimate for the rewards in any new direction you might want to consider. But unfortunately, this approach doesn't work in general. So if you have an arbitrary hypothesis class, the issue, which should be familiar coming from statistics, is there's no hope of constructing upper confidence bounds that are valid for every state or context, but at the same time shrink fast enough to get non-trivial regret. And that's actually true even for something as simple as like a single ReLU neuron. So instead, like another way that we can attack this problem, or another approach you can take, is since we already have these different models and algorithms that can do generalization in supervised learning, what if we could somehow reduce contextual bandits to supervised learning so that we can directly take advantage of these results? And we actually have a recent method that does exactly this. This is an algorithm which we call SquareCB, and I'll try to just describe it on one slide. So we're operating in this contextual bandit setting. T is the number of episodes, and I'm dropping like the H subscript here because horizon is just 1. So the way this algorithm works is at each round little t, we will get our context xt, and then we'll proceed as follows. So first, we will use a supervised learning algorithm to estimate the rewards based on all the data we've gathered so far. And just think of this as like an off-the-shelf algorithm for supervised learning. This could be like least squares. It could be SGD on a neural net. The reason we call this SquareCB though is because we usually use like least squares with the model of choice. But once you have this estimator, we'll call this f hat t. We're going to use this to assign a probability of being played to each action. And then we'll just sample the action from this distribution and update our learning algorithm with the data we observe. And so the main thing I still need to specify here is how do we assign this probability to the actions? And this we do using a technique called inverse gap weighting. And so the way this works is we'll first compute the greedy action, which we'll call B, that has the highest estimated reward. And for all the actions besides B, we assign them a probability with this expression. And I'll walk through this step by step. So if we're looking at an action A, we're going to assign it a probability that's inversely proportional to the gap between its estimated reward and the estimated reward of the greedy action. So this is like a reward gap. So I would call it inverse gap weighting. And then we're going to scale this gap by a learning rate parameter, which we call gamma. And then we'll add the number of actions here for normalization. And finally, we just give the greedy action whatever mass is left over after we do this for all the other actions. And that's how we get the action distribution. And again, we just sample from it and update the learning algorithm with the data we get. Okay. So what it turns out is Square CB actually yields sort of an optimal and in a certain sense universal reduction from contextual bandits to the supervised learning problem. So if you form these estimates using a type of supervised learning called online regression, you can show that for any function class, as long as you solve supervised learning or estimation optimally, this Square CB method solves the contextual bandit problem optimally. And I'll give a flavor of the result. So we're going to let SQ of t here, SQ is for square. This will just denote the total squared error between the estimators that our supervised learning algorithm produces and the true rewards for all the contexts and actions we see. And so what you can show is that as long as you choose the learning rate correctly, Square CB will guarantee that your regret is bounded by, the number of actions times t times this estimation error. So if you have low estimation error, you have low regret. In particular, whenever you can get sublinear estimation error, you can get sublinear regret. This root AT dependence is optimal in a certain sense, but it's easier to just walk through a couple of examples. So like for finite classes, you can show that the estimation error can be bounded by log cardinality of the function class. And this gives you like root AT times log cardinality regret for contextual bandits, which is optimal. You can do similar calculations for linear models. But the point is, as long as you're choosing the right algorithm for supervised learning, your regret is going to scale just with like the intrinsic complexity of your hypothesis class. And there's no dependence on the size of the context space because we're generalizing across contexts. And so like conceptually, the reason why this is nice is because it's really giving like a unified approach to designing algorithms and understanding sample complexity in this setting. And I'll just give a couple of remarks before I move on. So first of all, why does this method work at all? This is different from the other approaches we've seen, and it can't really be interpreted as like optimistic. And instead, what you can show is that this inverse gap weighting strategy, this solves a min-max optimization problem that links your contextual bandit error to your estimation error on a sort of like per round or per episode basis. And I can go into more detail offline, but this is really just saying in a direct sense, find me a distribution over actions such that regardless of what the true reward function ends up being, my instantaneous bandit error is controlled by my instantaneous estimation error. And the interesting feature is like why this works is this estimation or this min-max problem, it's completely agnostic to the structure of the hypothesis class you're working with. And I'll say more about this later, but this principle is actually useful beyond just contextual bandits. I'll just mention briefly on a historical note, contextual bandits have seen a lot of development up to this point. But these results like Square CV, where we can really like statistically reduce the problem to like classical supervised learning, these are actually pretty recent. And we're now just seeing these extend beyond contextual bandits to like full RL, as well as into production systems. Yeah, Costas, there's no distribution over context here. I mean, you can assume one, but you don't need to. Okay, cool. So we're coming to the last part of, or the last component of part one of this tutorial. And so the point is, we've seen how to solve exploration with a long horizon with no generalization. We've seen exploration and generalization without worrying about horizon. Now we're going to look at how do we do generalization and credit assignment, so long horizon, when we don't need to worry about exploration. And the approach we're going to look at here, which is, well, it's broadly from a family of methods which are called direct policy search. So as the name suggests, this is going to mean we're going to kind of try to like just directly optimize over policies that are good for our reinforcement learning problem, rather than say searching for Q functions. And here's the motivation. So when I talked about generalization and supervised learning earlier, we were taking a kind of classical perspective where we're assuming we have some minimizer for the training loss. We're proving some bound on the distance between train and test error. A kind of more modern perspective, maybe a little more in the vein of like deep learning, is just to say we have some big over-parameterized model, and we're just going to treat this as like a big stochastic optimization problem. And you can also apply this perspective to RL. So we're going to work with policies that are parameterized by some vector in R to the D. So pi theta will be the policy corresponding to parameter theta. And our goal will just be to find the parameter that maximizes the reward of pi theta, which I'm going to try to show you can think of as like a continuous stochastic optimization problem that you can optimize using first order methods like gradient descent. In order for this to work, the first kind of basic technique we're going to use is to work with what are called stochastic policies. And this just means policies that map states to distributions over actions rather than like discrete actions. The reason why we're going to use stochastic policies is that they'll give us a way to make sure that we have a continuous optimization problem. And typically the way we'll do this, I'm just going to give one example, is we'll set the probability that our policy pi theta selects an action A to be proportional to like softmax of some continuous function of our parameter and the states and actions. So like f theta here, it could be a linear function parameterized by theta, or it could be like a deep neural net parameterized by theta. But the point is, as long as f theta here is continuous, and we do some continuous map like softmax, this cost j pi theta will be continuous as well, and we can throw gradient-based methods at it. Okay, so let's look at how we do this.
Ilan, there's a question on the chat if you want to address.
Oh, really?
There's a distribution over context.
Oh, I actually answered that already. I mean, that's from the previous part, the contextual bandit part. Yeah. Cool. Yeah, so, okay, so we have this continuous subjective j of pi theta. How can we optimize this? You know, the first tool you might try here is just gradient descent. So like at each episode, you know, compute the gradient of this objective with respect to theta at my current iterate, and, you know, add this to the current parameter scaled by some learning rate. And the only question here is, how do I compute this gradient? So like j of pi is an expectation under this kind of complex process where we're running our policy and seeing how the system, like the MDP, evolves. And we're only seeing trajectories. Like we don't just have some oracle that gives us the gradient. But there's a really useful trick that we can use to estimate the gradient from trajectories. And this is called the policy gradient theorem. So what this says is we can write the gradient of this objective with respect to theta as an expectation under a process where we're running our own policy, so pi theta. And this is the expectation of kind of two terms. So it's the sum of the rewards for our trajectory times the sum of gradients of the log probabilities that our policy is assigning to the actions and states that are encountered. And the point here is both the quantities in this expectation are things that we can calculate based only on the trajectory we observe when we run our policy. And so we can get an unbiased estimator just by, you know, running for a bunch of episodes and approximating this expectation from samples. And I won't go into detail about how you prove this, but the basic idea is just you use what's called the log derivative trick. So this says if I have some function g of theta, I can write the gradient as the value times the gradient of the log. And like, why do you care about doing this? Well, the point is just to keep the value of pi theta around so that you can write this quantity as an expectation, which facilitates estimating from samples, like I said. All right, and that's the basic scheme. You know, estimate this gradient from samples, do a gradient descent update. as you can imagine, there are many variants based on changing either how do we do the gradient update, how do we estimate the gradients. But the point I'll emphasize here is like the policy gradient theorem is what's taking care of credit assignment, right? It's telling me when I see a particular trajectory and the rewards for it, how could I have changed my policy to improve the outcome? And I'll just give a quick sense for what the theory results look like here. I'll start by just saying a representative guarantee for the tabular setting. Even though our goal was to understand generalization here, this is the simplest setting to start with because I can pick a parameterization that lets me represent any policy, but this will still illustrate some of the key issues. So I'm going to pick a parameterization where I have a number for each state action pair that represents the probability. So theta xa is just the probability I select action A in state X. And what you can do with this approach is show that the suboptimality for any policy pi theta is going to be bounded by the norm of the gradient at this policy or at this parameter times a mismatch parameter that quantifies sort of how far the policy, the state distribution induced by the policy we're looking at is from the state distribution of the optimal policy. And so the point is, you can easily drive the norm of the gradient here to 0 with any first order method. And so the point to focus on is like the mismatch parameter. And you can think of this as controlling how much X you get to explore for free. So this is saying for a given policy, what is the ratio of the probability that we visit a state action pair under this policy versus the probability that we visit it under the optimal policy? And so you can think of this as capturing like how easy is your MDP to explore. So like if you passively visit any state, regardless of what you do, this parameter is going to be small. But if you have a domain where you need to systematically explore, it can be large. But the important thing to understand is like, this bound is actually tight. Yeah.
There's one question for you.
Just to understand, the ratio depends in the initial condition, because as it is, I cannot see where the policy takes place, because it's just the transition map of the...
Oh, sorry. Yeah, so just a note on notation. So P superscript pi is supposed to denote the probability that, you know, XH is X and AH is A when I run policy pi.
But why? I thought that this is predefined from the MDP that I am running, not from... Where is the policy that plays some role?
Well, what state you, like what state so if H is 1, this doesn't depend on the policy. But the point is like, you know, what the probability that I end up in a given state at time H is going to depend on all of the actions I've selected leading up to time H.
Okay, and that is the reason that I say that I assume that it is over all the probable initial states that you have take.
Yeah, that's supposed to be like incorporated into this expression.
Okay.
Yeah.
Okay.
Yeah. Cool. Let's see, where was I? Yeah, so the point I just wanted to say is like the fact that like naive policy gradient methods depend on this sort of parameter, like this is real. So you can construct even just tabular MDPs where the Ucbvi method I showed earlier will get sample complexity that's polynomial in all of the like problem parameters, but this mismatch can be, you know, arbitrarily large, really. But the point, like the reason we like this though is that like if we have tons and tons of data, this mismatch can potentially be okay. And the nice thing is like it's easy to scale these methods to, you know, bigger problems like continuous problems and incorporate function approximation. And I won't go into much detail on this, but the point is that like when you move to general function approximations, the style of the result you can get will say that like, you know, my suboptimality is going to be controlled by some parameter I'm calling epsilon opt, which reflects like how well you can do stochastic optimization, which is going to be related to like, you know, how flexible your hypothesis class is and how well you can generalize. Again, this will be scaled by a mismatch parameter. But on top of this, you'll also pay for some bias that reflects like, is your representation for these policies powerful enough to actually, capture the policies that it needs to for the underlying MDP. Okay. So I'll just briefly touch on the history here. So this idea of direct policy search, like optimizing over policies, this is pretty classical, but these methods have really had a surge in popularity in the last decade or so in the context of like deep RL, where we imagine that we're using like deep neural nets to represent these policies. And this is the approach behind a lot of the empirical successes we've seen for, say, like continuous control problems. I'll just say on the theory side, the idea of proving like non-asymptotic guarantees here has really only started picking up steam in the last couple of years. And I think there's a lot of really interesting questions here in terms of understanding like when do these methods actually work? What is really like the geometry of these problems? And how can you improve these methods by combining them with exploration? Okay, so that's actually going to bring us to the end of part 1 of the tutorial. I'm going to stop now, but when we get back, we'll look at how can we solve all 3 of these challenges simultaneously, like exploration, generalization, credit assignment, and we'll try to understand what is really like the landscape of what we currently know about RL theory. Okay, so I'll stop there and I can take further questions.
One question I had is, I'm not sure you went into like a more model-based approaches, like there was no like modeling of the actual reward function, like assumptions about the real world, like that maybe you can make that will help you in the
the only sort of setting I really went into so far where we did that was like the contextual bandits, where I'm modeling the reward functions. So that's all of everything we'll see in the second part of the tutorial is going to focus on exactly that problem though. And that's really kind of coming back to this point about like generalization. Yeah. Because like, why do you do modeling? You do modeling because you care about generalizing.
Thanks, Dylan. Thank you. So we're gonna have a half-hour break, and then the next session is gonna go out until 12:10.
Cool.